Another application of integration is arc length. And so arc length is a curved distance. First off, you have some experience with distance in that you know the distance formula between 2 points from all the way back in algebra. And so that's the direct distance. If I have, point A and I have point B, and I would find the direct distance between them, this formula will allow me to do that. You call one point x1, y1, and the other point is x2, y2, and you can find the direct distance, which is really a version of Pythagorean theorem. You create a triangle. You're basically finding the hypotenuse of that triangle, and that's your distance formula. Okay. Now, what if we wanted to find, though, this curved distance, okay, between 2 points on a curve, right? Well, that is called arc length, and we typically use S to denote arc length. You should have seen some of this in trigonometry, where you talked about the arc length around a circle, okay, distance around the circle, and we use that to define radians, etc. Anyway, so how are we going to do this? Well, we're going to do it through a series of subdivisions and adding up a bunch of smaller distances, just like we've done with area and volumes. To find a bigger area, we add up a bunch of smaller areas. To find a bigger volume, we add up a bunch of smaller volumes. So to find this curved distance, we're going to add up a bunch of smaller distances. So let's take our curve and subdivide it up into a couple of points on that curve. I could find the direct distance from here to here, from here to here, from here to here, okay? And I could add those three distances up. That would give me an estimate of what this curved arc length is. Then what I could do is I could subdivide it even more. I could say, okay, let's put all these points on this curve, and let me find the direct straight distance between each one of these. Now, the more of these I put in and I add up all these distances, it should get me closer and closer to the actual curved distance. And the more subdivisions I do, the more closer I get to the actual arc length. And so the idea generally is if we add up all those distances and then let the number of subdivisions go to infinity, we should get the arc length. So we've seen this happen a bunch of times now. We figure out what one of the distances would be. We repeat that over and over and over again, then let the number of subdivisions go to infinity. We get essentially an integral. And the integral we end up with for arc length would be this integral right here. And whether we want to do it in terms of x or y doesn't really make a difference. So if we have a function given by y equals f of x, and that's on a smooth curve. So a smooth curve generally just means we're going to talk about a continuous curve. It's a little more than that, but let's just say continuous curve right now. And we're looking at an interval on the curve between a and b. The arc length of f between a and b can be calculated using this formula. So f prime comes from the function we're traveling along, but we have to take the derivative of it. And a to b is the interval from where we start to where we end in terms of either the x values if we're integrating with respect to x, or y values if we're integrating with respect to y. And that usually depends largely on whether or not the function given was a function of x or a function of y. So in this case, determining which variable you should integrate with respect to is really determined by what kind of function you start with. So it's a fairly simple formula. I mean, hopefully this picture that we looked at explains where the formula generally comes from. But it's a matter of just applying the formula and getting the answer. And this formula really stems from this distance formula you see here. Okay, so you can see some of the relationships there. So let's do a few quick examples. So here we have this curve, y equals 2x to the 3/2 plus 3, which is this red curve, and we're going from 0 to 8, which would be here. So if we follow that up to the graph, here we're talking about here. So this is the curve distance we're trying to find the arc length of. So our arc length formula says that we're going to need to take the derivative. So we need to know what y prime equals. And that's pretty easy here. 2 times 3/2 x to the 1/2. Cancel the 2's, so just 3x to the 1/2. That's y prime. So our arc length formula is the integral from a to b of the square root of 1 plus y prime squared dx. So in this case, it's the integral from 0 to 8, that's the interval we're working with, times the square root of 1 plus 3x to the 1/2 squared dx. Well, in order to do this integral, I have to square the 3x to the 1/2, which will be 1 plus 9x, because I square the 3 and I square the x to the 1/2. So in order to integrate, I'll just use a simple u substitution. U equals 1 plus 9x. Du would equal 9 dx. We don't have an extra 9. I divide. So I end up with 1/9 integral of square root of u, which I'll write as u to the 1/2, du. So we simply get 1/9 integral of u to the 1/2 would be u to the 3/2 times 2/3. U, remember, was 1 plus 9x. Plug in 0 to 8, and we have our answer. So what are we going to get here? We're going to get 2 over 27 times, plug in 8, I'm going to get 72 plus 1 is 73 to the 3/2. Minus, if I plug in 0, I'm going to get 1 to the 3/2, which is 1. And I can't really do much more with this, so there's your answer. And that would be the measure of this arc length. Pretty simple. We don't really have a ton of examples we can do here because the integrals that result from a lot of these arc length problems are integrals that have a square root in them that are not very easy to do. And we need to work on some more integration techniques to be able to do a lot more of these integrals. So there's very few examples I can give you where the integration works out nicely. We can set them up and get to this point, but the integration, we're still lacking in our skills there. Here's another arc length problem. Here's your function. We have the log of cosine x. Here's the interval along that function we want to travel. So it's a function of x. Everything's going to be integrated in terms of x. These are x values in this interval. We're going to need to figure out what y prime equals. And so it's a logarithm, so it would be u prime over u would be our rule. So the derivative of the cosine divided by the cosine, that's your u. So the derivative of cosine would be minus the sine over cosine itself. I could write that as negative tangent. Remember, we're going to have to plug it into the formula. So whichever one you think is easier to plug into the formula would be the one you would go, whether you think it's easier to write the derivative this way or this way. So the formula for arc length, which we have this lowercase s, remember, is our arc length symbol. And so lowercase s, I say it's a lowercase s because it makes a difference when we use a capital S. Typically, we're talking about surfaces. So lowercase s is arc length. And we have the integral from 0 to pi thirds. My pen's not working. There we go. 0 to pi thirds of the square root of 1 plus the derivative squared. So this or this. I like the tan. So negative tan x squared dx. And it's just a matter of trying to do this integral. So if we look at this, we're going to have 0 to pi thirds. Again, my pen's not doing well. Let's try it again. Pi thirds. What do we get? We get 1 plus tan squared x. The negative goes away when you square it, but you get tan squared. So thinking about how we're going to integrate that. Well, 1 plus tan squared, if we use a Pythagorean identity, is actually equal to secant squared. So it would be easier if we wrote this as the square root of secant squared x. Now the reason why that's easier is because you're taking the square root, and thus the square root and the square will cancel, giving us just 0 to pi thirds of secant x dx. Now remember, how do we integrate secant? Well, we need logarithms to integrate secant, so this would be the natural log of the secant x plus the tan x between 0 and pi thirds. And this is well the main reason why you're going to have to make sure you know your integrals. So we can do something like this fairly quickly. So I'll plug pi thirds in here, and then I'll also plug in 0 and subtract. I'll bring it up here so we can do it. So what do we get? We get the natural log of secant of pi thirds. So you should know cosine of pi thirds. And then we're going to do the secant. Cosine of pi thirds is 1/2. So secant would be 2. Tangent of pi thirds is square root of 3 minus the log of secant of 0. Cosine of 0 is 1, so secant's reciprocal, so secant would be 1 as well, plus the tan of 0 is 0. Now notice that this ends up becoming the natural log of 1, which actually ends up equaling 0. So these are all little things you've learned along the way, so basically all that shit drops off. So we end up with the natural log of 2 plus the square root of 3. Now 2 plus the square root of 3 is already positive, so I don't really necessarily need these absolute values on here. If you left them, it's okay. But there's your measurement for the arc length. And again, leave your answer like that. I don't want that decimal answer you get when you plug that in your calculator. What you're going to find is that at this point, there's not a whole lot of examples I can give you because we're limited in the amount of integration we know right now. And so a lot of these arc length integrals end up becoming integrals that we don't quite know how to integrate yet. So we could at least set up what the integral will be to give us the arc length, and here's an example of it. But you're going to see that this is going to turn into an integral that we just can't do yet. And so this is a function of y right now. So we're going to do everything in terms of y. You see we get this parabola. We're going from 0, 0 to 1, 1. Okay? And if I thought about this in terms of y, I would figure out what x prime equals, which would be 2y. And so my arc length formula would be the integral from, think about the y values we're working with here. We're going from a y value of 0 to a y value of 1. So that's the integral on y. And we have the square root of 1 plus the derivative squared dy. And you see what we end up with is integral of 0 to 1 of the square root of 1 plus 4y squared dy. Now here's the problem. The problem is that this integral is not something that we can work with right now. We will be able to do this integral in the next unit using what we call trigonometric substitution. But right now we don't have it. I mean, all we really have, our big integration technique that we have right now, is to use substitution and turn it into one of our basic integrals that we should know. And there is no substitution that's going to work here, because the only substitution you use would be some piece or all of this thing inside the square root, the radicand. And if u equaled 1 plus 4y squared, du would equal 8y dy. And the 8's not really the problem. We can fix that. But having this extra y, we don't have an extra y anywhere in this integral to make this work out at all. So, at this point, that's as far as we can go. The only other thing we could try is to try and do this as a function of x instead. So if you think about this, that equation is the same thing as y equals the square root of x. If I want to do the arc length formula in terms of x instead of y, I could. So I got to figure out the interval of x's. Well, the interval of x's are actually the same. It's 0 to 1 on the x-axis. I have the square root of 1 plus. Then I need to know what the derivative is. So y prime. Well, this one's going to be even worse because it's going to be 1/2 x to the minus 1/2. So I'm going to end up with 1/2 x to the minus 1/2 squared. Okay, dx. And so I end up with the integral 0 to 1 of 1 square root of 1 plus 1/4 x to the negative 1 dx. And so, you look at that and you go, well, that doesn't look too bad. But there's no u to u going on. I could try and rewrite this inside of the square root and say this x is really in the denominator, so it's really 1 plus 1 over 4x. I can try and write that as a single fraction inside the square root. Maybe that'll help. That's not going to do anything though. I would have 4x plus 1 over 4x. I'm still not getting anything that's going to be able to be integrated. So whether I integrate this, or this, or this, or this, I don't have anything that'll benefit me. So while we can set up the integral and either say this is the integral or this one here is the integral, or any version of that, we can't really get to the actual answer for the arc length with the knowledge we have of integration right now. So it's a slight downfall of covering this now instead of later, but at least you have the idea down of how you would calculate arc length. And we have a couple of examples we did. There's some examples you can do, but a lot of examples we need a little bit more integration. So you see how much we still have left to cover.